we want to talk about reading potential energy curves. So one of the things that I've tried to say up to this point here is that Newton's laws is not the way to really go about this. And the reason why Newton's laws is not the way to go about this is that it really is the hard way to actually view physics. And one of the most, mind-blowing ways of looking at, what happens in when we use energy is that it really changes the picture dramatically. And so what I want to do here is that I want to go in and say, what do I mean by this dramatic viewpoint? And we're going to start off by, what is a conservative force? A conservative force defines a potential. What does that mean in terms of forces? So here we go. So if a force is conservative, then we know this must be true here. We know that the work done by a conservative force, this work is the line integral, and this is equal to the negative of the potential function. What we're going to focus on is not this thing, which is what we've spent a lot of time on. What we're going to focus on instead this time, we're going to focus on the force. And when we focus on this here, you're going to see that we can relate this thing to a force if we wanted to. But what we want to do here is that I want to look at something slightly different here. So what we're going to do here is that by plotting u of x versus x, the potential energy function, we can say what behavior a mass will undergo while in a, and this is a hard way to write this, what is called a potential field. The problem is the word potential and potential energy are two different expressions. They do not mean the same thing. We're really plotting something called the potential function. Unfortunately, whoever gave the word potential, the word potential has given it the most hideous name possible because, of course, students are going to interpret potential and potential energy as being the same thing. That's why I call it a hideous thing. So let me show you what I mean. So what I'm going to do here is that I'm going to talk about the gravitational potential, and I'm going to talk about the spring potential, and then I want to go to an example. So the first thing I'm going to do here is I'm going to talk about the gravitational potential. So note that this is not in the book. This is really a more advanced way of thinking of something. But once you get a feel for it, God, it makes life so much easier to do. So there's a couple of things that are really important about potential functions. There's the force picture, and there's the potential picture. And what we find here is that when I think about the force picture, let's say that I'm going to drop a ball. Or let's say that I'm going to throw a ball up and the ball is going to come back down. So as an example, we're going to throw a ball up, and of course, it goes up and comes down. So what do I really envision here? Well, there's two pictures, believe it or not. And the first picture here that I'll look at is the force picture, because this is the most conventional picture. But my remark here is that this is the worst picture possible. So when I look at the worst picture possible, what I'm going to imagine here is that I throw a ball up from the ground. So what I'm going to do here is that I imagine that this is the ground. And we all know that if I throw something up, it comes down. But why does it come back down? Right? What a silly question here, right? It comes all the way up to here. And I'm giving it some initial speed here. And we all know that the reason why is that there's this thing called the force of gravity. We know that the force of gravity is always acting on this thing. And it gets up to the top. And we know it reaches a speed of 0. Then the ball turns around, of course. And then the ball does what? It falls all the way down till it almost hits the ground. And we know that the velocity of this thing is going to be equal and opposite to the initial speed, but it does something like that. And the reason why, it's because, of course, the force is slowing it down. And if the force is slowing it down, it decelerates it, and then it speeds it up and coming back down, and that's it. That's your picture. That is not the energy picture. Okay, the energy picture is quite dramatic. So let's go look at this thing here. So what I'm going to try to draw here simultaneously is that I'm going to come down and I'm going to draw the energy picture. I would love to draw them right next to each other. So I should be careful. I should not be saying energy picture. I should be saying the potential picture. So what do I mean by that? Well, for starters here, in the world of energy, what we're doing here is that we want to plot gravitational potential versus position. In this case, I'm going to call it y. And so when I look at this picture, what does it really mean? Well, what we're seeing here is, so if I plot this, what am I really plotting? I'm plotting this function here, right? So I have this function that looks like this, and I have what? UG is going to be mgy. And so when I look at this plot, what does this plot look like? It looks like it's a line. A line like this. And so what you're seeing here is that if I look at this guy right here, this guy is an incline. And this is where I'm plotting y. And what you're seeing here is that in the energy picture, which I've started showing you already, look at what happens to the ball. What does the ball do? It starts here. Where's it in the energy picture? It starts here. And what happens to the ball? It goes up and it goes to its maximum height. Where's the ball in the maximum height picture? Right here. So when a ball interacts with the potential energy function, it does not go straight up and down. It goes up in a gravitational ramp or incline. And so what you're seeing here, as the ball goes up, just like the ball goes up, in the energy picture, it goes up a ramp. And you know that it cannot go forever, right? It cannot go forever. So if I wanted to translate the force picture onto my potential picture, then look at this here. So the first thing that I would do here is that from the potential energy, I should be careful, gravitational potential energy function, we know what? Well, we know that U of G is equal to mgy. Therefore, according to what we wrote before, the negative of the gravitational derivative with respect to y is then going to be, right? I take the derivative of this thing. Clearly, I take the derivative of y, that's 1. I'm going to get minus mg, and that's what we identify as gravity. So what you're seeing here is that du g dy is the slope of the gravitational curve here. And so what you're seeing here is that the slope is positive, but the force is negative. So as the ball moves up the incline, it applies a force of gravity in the negative direction. And because this slope here that we're looking at, this is a constant slope, that implies that the force here will always be a constant force. And therefore, it looks like that. And so you could see here that when we get to what you're finding here is that look at the direction of the velocity. The velocity of the ball is going up the ramp. So what does the force of gravity do? It slows it down. Why? The force is in the opposite direction. And you know what? I should be really careful here. This is known as the forbidden region. This is the classical forbidden region. And what that is here is that just what it's really saying is that the ball can never go inside the incline. It's an energy field that it can't do that. So as an object interacts with the potential energy function, it does encounter a force. So if the potential function is not zero, then the force is not zero. But that's really what the picture is right there. So why would we want such a picture like this? Okay, and the answer is, once we know what the potential energy of an object is, we know immediately what actually happens. So as an example here, let's draw a picture like this. So if I look at this thing, imagine that I have an incline. Okay, here's my incline right here. And then I have an incline that goes up like this. And then it goes like that. It's a constant. So what you're seeing here is that there's really 3 regions. There's a region where we're going to say that that's where the potential energy function is. And again, what actually happens here is that there's I don't want to do that actually. I think what I'm doing here is wrong. You could see that there's a region where I have an incline, and then there's a region where it's flat. And maybe what you have here is that you have a ball right here. And you want to know whether this ball can actually get up to here. So a very good model of this is that we could think about a rocket leaving the Earth's surface. So what you're finding here is that the green shade actually represents the Earth. The black shaded area represents, let's say, empty space. Now, is it really empty? Of course it's not. But we're just going to be looking at this thing. So if I wanted to escape the Earth, what do we actually need here? Well, picture-wise, we could come in and we can draw bar diagrams. If I really want to escape the Earth, I need a minimum kinetic energy to do that, right? This is the minimum kinetic energy. Now note, this is a model without any drag, but of course that can't be. And the reason why that is because you could see as the ball is moving up the incline, ooh, that Earth is going to be in the way. So I'm going to eat that thing up. You could see that a piece of this is, of course, the potential energy, right? This is going to be the gravitational potential. And the rest of it, since this is the total energy of the system, looks like this, right? This is the rest of the kinetic energy. But what you're finding here, as the ball goes up, what happens? Well, as it gets to empty space, a lot of that energy had to be expended to do what? Escape Earth's surface here. So, but to escape Earth's surface, you got to make sure that you have a little bit of extra kinetic energy to actually leave the orbit of Earth. And so you got to agree that this picture is considerably easier than trying to deal with Newton's laws, because the gravitational force is actually proportional to 1 over r squared. In other words, F of r is proportional to 1 over r squared, and it's a complicated 1 over r squared. That's just a simple one. So this means that this is not a constant force. So this requires now differential equations beyond Math 7. And Math 7 is the differential equations class at Cabrillo. And so, but with the energy picture, what you see is exactly what you write. It's a very, very, very powerful image. So that's one way to think about it. The other one that we could think about is the spring potential. And we've already spent a fair amount of time on the spring potential, so I'll try to do this a little bit faster here, and let's see what we have. So I have the force picture. And so when I think about the force picture, the picture that we drew had something like this here. We had a cart, right? In this case, I'll continue with purple. I'm feeling purple today, I guess. And what you find here is that I have 2 springs. And of course, this is my equilibrium. So as this thing moves back and forth, you're finding here is that the system is always encountering a spring force in this direction or that direction, a spring force in that direction or this direction. So you're really having to deal with a system of 2 coupled forces here. And what we said here is that that's what we see. We see the force picture in everyday life, but that's not what we want to be looking at. What we want is we want the energy picture because it's more powerful. And just like we use the energy picture over here, we do the exact same thing. We plot the spring potential and then reinterpret it as an energy field, a potential energy field. So now we have the spring potential energy plot, or picture, I should say. Or maybe I should just say energy picture, because I think that's what I've been saying. So if I look at that energy picture, we don't look at it this way. What we have here is we have a parabola. Let me try that one more time. And this parabola, what we find here is that when we look at this thing, we have this energy field. And a cart cannot move into the forbidden region. And what you're seeing here is that this is the forbidden region. Just like the other side. You can't go through this super thick area of energy. And so when I look at this picture here, the reason why I got that is that, as we said before, I have a spring potential that's 1/2 kx squared, and I'm plotting this relative to x, where I have my equilibrium right here in the middle. And so what happens here, how do I interpret this in terms of the forces here? So if I have a force, we already said that the force was equal to the negative derivative of the potential function. And you could see here is that when I take the derivative of x, I'm going to get a 2. They cancel out. So then I'm going to get minus kx, which is exactly the spring force. So that means as I move in which direction? So imagine that I'm moving my cart in this direction now. Right? So here it is. And my object is moving where? In that direction, away from the equilibrium. Look at the slope of this guy now. Okay? Look at the slope. If I look at the slope here is what? It is a positive slope. Right? This guy is a positive slope. Since this guy is about slope, the force is then in the negative x direction. That implies here that there's going to be a spring force. Where? In that direction. It's in the opposite direction of the velocity. Okay, so one more time here. Since the slope of this guy is positive, then that tells me that the force here is negative. The spring force is negative. That's what we would have expected. And if the car is moving in the opposite direction, like this, then if I look at the slope of this guy, you could see here that the slope of this thing looks like this. So this guy is a negative slope. But if it's a negative slope, then this tells me here that if the spring force is negative, then if the slope is negative, then the spring force has to be pointed positively. So then I could see that the force is then pointed in the positive direction, and it slows it down. And so if I look at my spring, so if I take a cart and I now release it, okay, so then if I do this as an example of energy conservation, let's imagine that I have my system here. Okay, so what I'm going to do here is that I'm going to take my cart I have 1, 2, 3. So here's my equilibrium. And what I'm going to do here is that I'm going to bring my cart all the way over to right here. And I'm going to start this at rest. Okay, so at this point here, you could see that this is a very loose string. This spring is very tight. So in other words, I'm saying that this guy right here is a turning point. So what does this mean in the picture here? So what I imagine here is that I have this type of thing. And I could see here that here's my equilibrium point. And my cart is starting where? Right here. And I know that this guy is starting from rest. So when I draw my potential energy function, what does it look like? Well, I know that I'm going to set my potential energy function to be 0 right at the equilibrium point. So at the equilibrium point, that tells us that the spring potential is 0. So when I look at this thing, my bar diagram says, well, it's got to be, that's how much potential energy I must have. It has to have that amount of potential energy. So that means, since that's the total energy of my system here, then that means as this object falls, you could see that I'm converting potential energy into kinetic energy. And as it gets all the way down to the bottom, we know that we have maximum kinetic energy. And the reason why we know we have maximum kinetic energy is because the potential energy at this point right here is 0. And then we ask the question, how high could this possibly get? If there's no friction being taken out of the system, then it should come to the exact same height. This picture is considerably easier